Hello. My name is Brock Palen. I'm the Associate Director for what we call Advanced Research Computing Technology Services. Specifically, I'm responsible for all of our high-performance computing and large research systems at the University of Michigan. We focus around data, compute, analytics. First, I'm going to tell you the story about the way computing is organized at the University of Michigan. Under the Office of Advanced Research Computing, we actually have these 4 different organizations that all report up through the same person, and we all work together. Specifically, we have 2 faculty-led institutes, of which I'm going to be focusing on one today. You can probably guess because their banner's on the bottom of the page and will be on the bottom of all of them. And then we have 2 service organizations. So we have a MICDE, the Michigan Institute for Computational Discovery and Engineering. The faculty in that, unfortunately, couldn't be here today because their annual symposium is tomorrow, and there's no direct flight to Detroit from San Jose. So I got sent here to tell you about all the work. Now, I was involved with the proposal that funded this. The university also has a very large investment into data science. A while ago, the university announced our Data Science Initiative, which is a $100 million investment into data-intensive computing, analytics, training, and outreach. The faculty that are involved with that are generally organized underneath the MIDAS, the Michigan Institute for Data Science. You see the technology services, which is the group that I represent, and I'll skip over that quickly because most of us here know what that generally means. But the other key thing we have at Michigan is a group called CSCAR, the Consulting for Statistics, Analytics, and Computing. This is actually one of our real value adds, that we have a group of PhD-level consultants available that faculty can work with. So we heard earlier that it's, you don't want to have science people focusing on application stacks and different types of hardware and how to move data around and stuff like that. And we can actually do a lot of that. We have all that expertise in-house. So Michigan is uniquely positioned to be able to bring all these efforts together and have them organized. When we announced our data science initiative, I won't name any names, but a number of my peers in different academic computing organizations reached out to me and said, like, hey, U of M, I just saw this announcement. Did they set aside any budget for compute? And it's like, actually, we did. We set aside budget for compute, outreach, and consulting. Something that is unique to something we did at Michigan. So what's something that we've recently worked on? So in MICDE, we've created the Center for Data-Driven Computational Physics. Now, before I go into this too much, when I was an undergrad, I had the luxury of hearing a talk from Guy Kawasaki, who was known as being the marketing guy behind the original Macintosh. And in his talk, he talked about innovation, and he talked about the way that people, generally, you grow when you have revolution. So an example of this he used was the keeping food cold industry. And so originally, people cut ice from rivers. And innovation for the longest time was bigger saws, more horses, move more ice. They didn't see the refrigerator. This is our attempt to make the refrigerator. So up till now, we've been doing bigger machines, and we keep doing direct analysis, and we keep finer resolution, larger scale, more physics into calculation. In this case, we're trying to actually combine data, machine learning and stuff, and apply it to traditional computational physics. We hope that with this sort of system, we can be able to move forward and do more scale and higher order models with a modest set of resources, so that when we have the larger resources, we can do, again, yet more. So what happened here, though, is a traditional high-performance computing platform doesn't necessarily serve the needs of what we're trying to accomplish. And so you can see here, Dr. Durasamy, who is the director of the center, said it merits new hardware, configurations, software, and computational methods. And so that's why today we partnered with IBM to be able to tackle these different research areas. These are the research areas we're focusing on. As you can see, they're all the classical computational physics problems that we've heard of many times before in high-performance computing, but we're tackling it with a machine learning approach. In a number of these cases, we're going to be taking in data from sensors, observations, as well as large-scale simulations from classical large-scale systems to be able to train data sets, to be able to have the trained data set that we can use to be able to actually deploy an application that can run in a much more efficient manner. So here's the actual details of what we're getting. It's a much more modest machine than what's going in at the DOE labs. But if you notice, there's a bit of similarity here. We have, the key component here is actually what we call the garrison. Now this is a machine that has NVLink between the GPU to the host processor. Everything about this system is optimized for data movement. 100 gig InfiniBand, the best you can get right now. Power 8, highest memory bandwidth per socket you can get. NVIDIA NVLink, highest speed you can move data from accelerator to and from host memory. And of course, the NVIDIA Pascal GPU that was announced earlier, highest memory bandwidth on the accelerator. Everything about this is about speed of data movement and for total aggregate performance. And so what's unique about this system is you heard a couple of things earlier. One of the key things we figured out we needed to be able to run Hadoop Spark-style workloads alongside traditional computational physics workloads. So this entire system is designed around the ability to be able to access data from two different paradigms because of the existing application stacks that are out there. We needed POSIX access as well as HDFS API access. We needed to be able to run Yarn containers, and we needed to be able to run MPI run to be able to launch a traditional parallel application. So this entire system from the scheduler stack through to the file system is able to be able to support all those different types of workloads in a single location. Something else we are working on, and by the way, I'm not going to use any of my time here, so if you have questions, feel free to ask them at any time, is we're very interested in keeping an ecosystem alive for multiple ways to be able to run applications. For this, we've been working actually on creating a program in which we can encourage students and people in the community to be able to port common scientific applications to the Power platform. This is the platform we've chose to try to increase adoption of, and we are happy to partner with that. So this is the usual way you can contact us. You can find us on arc.umich.edu. The University of Michigan has a $1.3 billion research budget. It is one of the largest research budgets of a public institution in the entire country. We're unique in the sense that we have a very large hospital, as well as a very large engineering and a very large liberal arts school. In fact, we have 101 top 10 graduate programs, which is, again, unique in the country. It's very rare to find schools, let alone one that has over 100 top 10 graduate programs. So one of the challenges are that when we look towards, we're building this platform for this specific use case, is that we're always thinking about how can we handle data, compute, viz, analysis, training and outreach, networking, to be able to meet all these different domains and needs that exist on our entire campus. And of course, the university also has many, many collaborations. We're leaders in transportation, medicine, physics, engineering, and social sciences.